Chapter 18, Part 7. And diving into Chapter 19, because 19 is some of the background you need for the latter part of Chapter 18. And so, in our previous lecture, I started talking a little bit about this reaction. LDA, deprotonates, so you can draw it as the salt, or you can just draw lithium. And there are certainly lots known about making E or Z enolates. We're just going to draw it as the enolate and pretend that that we know that it's a mixture of those. And then you throw in ethyl iodide, and you get alkylation, and 90% yield or better. So this is a really good reaction. As I was saying, that this particular step right here is actually critical, because LDA is a very strong base, and the pKa between diisopropylamine versus an ester is 25, 35 or more, and so this is an irreversible. So you get, and you can get, if you go in with a slight excess of LDA, you will completely convert the ester to the enolate. Now, before LDA, we didn't really have a good, super strong base, but we had things like alkoxides, right? And you could use that. So now I've switched to the sodium salt here, but because lithium methoxide is not a very soluble base. This is usually done in methanol, and again, for solubility issues, and the pKa of methanol is about 16, right? So that's less acidic, than the ester, and so if you treat the ester with sodium methoxide, you get much less than, right, 9 orders of magnitude, 1%, right? But, and so this is a very extremely reversible reaction. And so what that means is you throw in sodium methoxide, and you stay with methoxide, because this also will be attacking the carbonyl. That never happens with LDA because of the sterics. But you won't, that's a background reaction. So we have these somewhat acidic protons out here, and sometimes you'll deprotonate that. So what that means is you have less than 1% of sodium methoxide, or sodium, this enolate, in a vast ocean of ester. And so when you add something like sodium methoxide to an ester, you'll set up this equilibrium, and you won't have if you throw in methyl iodide, not much will happen, because you've got a very small amount of the enolate and a lot of methoxide. So maybe you'll make dimethyl ether rather than alkylating this. But what you will get, because you've got all this ester in the middle of this enolate, is this enolate will attack the ester. So, and this kind of gets us into chapter 19. And isn't it interesting that most of we draw the enolates with a charge on oxygen, yet their reactivity is on carbon. But that's a discussion for another day. Right, so this is a methyl butyrate, 1, 2, 3, 4. So we have addition, and then of course methoxide leaves, right? So we've gone in with sodium methoxide. We get it back as soon as this acylation. It's not an alkylation, it's an acylation of the enolate. So we get this back. But now we have a beta dicarbonyl. And beta dicarbonyls have pKa's between somewhere between 10 and 13, depending on whether they're both, you have a ketoaldehyde, a ketone, a keto ester, a keto amide, a keto nitrile. All of these qualify as beta dicarbonyls. They're far more acidic than esters, and they're more acidic than methanol. And so as soon as you form that condensation product, you will deprotonate that and get your methanol back. So this is a reaction that consumes methoxide, so you need to go in with more than one equivalent, and you get this beta dicarbonyl product. Now you can add acid and isolate that that beta keto ester, and recognize that if you enolize the ketone, and it's really the ketone which will enolize, you can form a hydrogen bond between the OH and the ketone, sorry, the ester carbonyl. And now you have this lots more resonance structures. So there's a tendency for these things to enolize. Now we're talking about thermodynamics here, not kinetics. And what's important about beta dicarbonyls is if you take them and treat them with a moderately strong base like sodium methoxide, you will get your enolate back. And then if you go in with, and you get 100% of the enolate, because again, the pKa's are so much different. And and you can alkylate it. And then if you take and you treat it with sodium hydroxide, you can hydrolyze the ester, and then oops, sorry, you get the